Here we are once again. This is the Physics 2A video lecture. Physics 2A video lecture 10. So let's start off with some announcements. And of course, the announcement that it's on everybody's mind is, what about the exams? The exams are partly graded. I've made great headway, so they will be, the scores will be in your mailbox sometime middle of the week. No problem there. Okay, so we've got the exams. We took the exam, and then we're starting lectures 10, 11, and 12 this week. And the homework, the notes and the homework will be due Friday, the 24th, the way we've been doing all the time at the end of the week. So yeah, keep taking good notes. I've seen so many good notes that it's a great thing. Take good notes. Okay. Anything else? We're going to start off with the review of what we had talked about in chapter 10. We're doing thermal physics now, so I'll go through what we had talked about and then continue on with that. So here we are with thermal physics, and I like to give a certain progression here of ideas, and we'll repeat that. Namely, that we start with the sensation of hot and cold. That is the beginning of thermal physics for us. And then we associate phenomena with hot and cold. And the associated phenomena are of hot things and cold things, fires, cold water, ice, cold weather, warm weather, things that we actually sense and then associate. So we have phenomena, and I'll just say fire, ice is good because they go with hot and cold. And then a third point is that we have other phenomena of hot and cold that go with these. And those are, for example, thermal expansion. So thermal expansion is a little more subtle than just feeling things that are hot and cold. Yeah, I had brought some demos in last time, and I'll just remind us what I did. I'm not going to repeat them, but we had a ball and a ring, and the ball won't pass through the ring. I apply the torch to the ring here, and this thing gets hot. Not so much that you can see it expand, but then the ball, which is a close fit to begin with, will pass right through. And so then we say the application of heat has made this thing expand. And I also showed the bimetallic strip. So we'll leave that there, having seen that. Actually, I'll take these back off stage. And what this allows us to do is get thermometers. So I can bring a thermometer, and I'll bring this contraption that we've seen before. So then I have the gas thermometer device here. Okay, so I'm going to discuss this a little bit more. So yeah, we have the thermal expansion, and then in our list here, we get thermometers that make use of thermal expansion. And having a thermometer, we can then invent a temperature scale. Okay, and there's more than one temperature scale, so I put the plural for temperature scales. Good. Now, before I get to the gas thermometer, let's just talk a little bit more about thermal expansion. There's a section in our book in which this is quantified. So different materials have different thermal expansion properties. And the bimetallic strip was an example because two metals, one that expands more than the other, were pushed into a bent mode. As you may recall, it's on the old video. Okay, so we have to talk about that a bit quantitatively. And I'll go ahead and put that right here. So talking about thermal expansion, we have linear expansion. So all of the linear dimensions of an object will expand when heat is applied, or when its temperature is increased. And the expansion will look like this. L will equal L0 plus alpha L0 T minus T0. That's the formula for thermal expansion. And what it means is if you have some object here of length L0 and you apply heat to it, it gets a little bit longer. This meter stick, if we heated it up, would actually get a little bit longer. But how much longer? That depends upon this coefficient of thermal expansion. Now, we can also subtract the L0 over and write it this way. So L minus L0 is delta L, then that's alpha L0 delta T. So this is a more compact form. I'm going to recommend a couple of problems in the homework where we just actually plug in some numbers. This alpha is the coefficient of thermal expansion. Coefficient of thermal expansion. Okay. And what do we always do when we introduce some new quantity? We ask, what are the units? And the units here we get by saying, what do we have here? We have, here I'll stand right here, we have lengths and we have lengths. So those would cancel out. Alpha and delta temperature have to be dimensionless. The product of the two has to be dimensionless. So the units of alpha are inverse degrees Celsius. So I'll just put here alpha units 1 over degrees Celsius. Okay. So those are the units. Go ahead and look in your book. There will be tables of these. They're very small. They're on the order of 10 to the minus 6, 10 to the minus 5. So that if you heat this thing up by 100 degrees Celsius, it may have an increase in length of 1 millimeter, okay? Which you wouldn't just see looking at it, but that could have repercussions. Good, so these type of problems are mainly just plug it in type of problems, but they're interesting if you just do a couple of them. Good, so we'll have the linear expansion. That may be blocked by this object no longer. Okay, so linear thermal expansion. Couple of homework problems. I'll write those down later. Yeah, so what is next in this progression of ideas? We have the thermometers and the temperature scales. Next, I'm going to talk about the gas thermometer. Gas thermometer. That's the device I have here. I'll keep these points on the board and erase this. Okay, so what about the gas thermometer? We had this here last time, and I'll just explain how this thing functions. We've got a tube open to the atmosphere, so there's atmospheric pressure. If we heat this up, as you recall, this red fluid will come up here. And in fact, we know about pressure and atmospheric pressure. If you just think of a vertical column of fluid, okay, then rho GH gives us the pressure at the base of that column of fluid. Okay, the pressure depth formula. So yeah, we have pressure depth formula here. This isn't exactly designed as a gas thermometer. I'm just using it to illustrate the property. Over here, we would have just some gas, and it wouldn't have to be air. It could be a different type of gas. And I put it in here, this beaker. It symbolizes that I could have this heated to boiling or freezing or whatever other temperature, and I would be measuring that temperature with this thermometer right here. Okay. So that's the idea with the gas thermometer. And what it allows us to do is get the pressure as a function of temperature. So the section on gas thermometer, I can't leave it out altogether, so. Gas thermometer, I want to do a bit of this discussion. Okay, so you've got the gas thermometer. Here's your beaker with this bulb over there, and we have a thermometer sticking out that we can measure the temperature, and we bring it to another object here. So this is a schematic of our gas thermometer. Let's say I have a real one, and then we have a column open to the atmosphere. Okay, today's a good day to have different color of ink here. So suppose we have a fluid in here, not red but blue in this case, all the way up to here. So these two levels define a height. Okay. And of course we know that P is equal to P atmosphere rho GH for this fluid. But that pressure is the pressure of the gas in here. Okay. See these lines again? I'll go ahead and go into here, into here. And to do this right, technically you have to have what's called a constant volume gas thermometer. You have to keep this volume constant. And the upshot of this experimentation is that you've got a temperature and you've got a pressure. The temperature increases, the pressure increases. So let me draw a graph of what is discovered in these situations. Actually, before I draw the graph, I'll write a couple of words here so we can have, if we hold the constant, if we hold the volume constant volume, then we can get pressure as a function of temperature. And if we hold the temperature constant, temperature equals constant, then we can get, so we hold the temperature constant here, we can get pressure versus volume. Okay. We can get pressure versus volume. So if we had the constant temperature, then we'd increase and decrease the pressure on one side and increase and decrease the volume on the other. Okay. So that's what this gas thermometer type of device will do. So let me go ahead and take this away now. And I'm going to do pressure versus temperature for different gases. So when you draw this graph, you actually have to leave a lot of room on the left side of the graph. Okay, so temperature in degrees Celsius, pressure, I won't worry about the units. If we have, I'll just say we have 0 and 100 degrees Celsius here. And you know the pressure increases with the temperature. That's why I have a positive slope. If I extrapolate this line, it's a straight line, it ends up somewhere here, okay? Now I can do the same thing with a different gas and it'll have a different set of data points. But if I extrapolate its line, it also goes to the same spot. And so what's interesting is you have this linear law for pressure versus temperature, and it would be simplest if you called that your 0 point. If you called that your 0 point, then you would have just a simple equation of a line. And this thing here is T equals minus 273 degrees Celsius. which is then identified as absolute zero, and the absolute temperature scale is then called the Kelvin scale, and we have T Kelvin is equal to T degrees Celsius plus 273. So that's the absolute temperature scale, the Kelvin scale. Okay, so that's kind of interesting that that even happens like that. First of all, linear is a nice simple relation. And this is for a gas thermometer, so I can already say here, ideal gas. Probably heard the ideal gas law before in your chemistry class. Okay. So this would be one part of the ideal gas law, and the gas thermometer could be used to get the pressure versus volume behavior as well. Okay, so this type of experimentation leads empirically to these kind of laws here. So I should label this. This is some type of gas. We'll just call it A, and this is another gas. Call it B. They could be hydrogen and helium. They could be oxygen, carbon dioxide, any number of gases. They'll have this behavior here. So what we get is the ideal gas law. I'll put it in what I call the chemist's form. Ideal gas law. We have a good section on this in our text. So you'll find everything you want to know about it there. What is found is pressure times volume is proportional to temperature. So number of moles, gas constant, and temperature. The temperature has to be measured in the Kelvin scale to have this very simple law. Okay, if you held the volume constant, pressure was proportional to temperature. Okay? If you held the temperature constant, pressure was inversely proportional volume to volume, inversely proportional volume. Okay, so there's the ideal gas law. Look this up if you want the numerical quantities here. It's for us. It's important to know that this is temperature in Kelvin degrees, not Celsius. And the reason we can do that is because of this property. This graph is obtained using ideal gas and gas thermometers. Good, so far so good. Now, we'll think of this as the empirically derived law, and what we want to do is some theory to try to explain the form of this, okay? Now for that, we have to have the idea of atoms and molecules, and I'll just say atomism. That's the idea that there are very tiny, invisible, in fact, constituents of matter. Atoms, molecules, I just refer to atoms. But it was the chemists who actually had this idea first, although actually the philosophers of classical antiquity actually had the ideas of atomism before anyone, a couple thousand years ago, without any particular exact theory of it. Okay, so what we're going to do is assume this idea of these tiny particles. And what do we know? We know mechanics. We know that things fly around and bounce around. So we're going to use mechanics of these tiny invisible particles to try to understand the ideal gas law. So I'll write here atomism, and we'll write molecular motion, or so I want to just stick with the word atom, we'll just write motion of tiny, and when we say tiny, it turns out they're very, very small. Tiny particles. And of course, what do they have if they're moving? They have kinetic energy. They have kinetic energy. So I could write, the kinetic energy is 1/2 mv squared. Even though I can't see these, I can't feel them literally. I'm just assuming there are these tiny particles, for example, of gas, of air, and they're moving around. So what follows now is the derivation or the discussion of the ideal gas law in terms of little particles. So let's have a look at that. Yeah, what we're going to think of is a large number of particles just in a box. So let's write here, next, n, a large number of particles in a box, okay? And the idea, we have to have a couple stipulations here, but I'll go ahead and draw a box. And it has sides of length L, L, and L, so the volume is L cubed. How's the perspective on that? You gotta be a little further away. All right, we can deal with that. Okay, there's the box. There we go. Okay. So we have n particles in there, and the individual particle volume is so small that they would fit into a tiny corner of the box. That's the nature of a gas. If you take air and compress it, say liquefy it, the air in this cube here would just fit into a little corner. Okay. We learned about the density, right? Density of water is 1,000, density of air is 1.3 kilograms per meter cubed. So it's literally close to 1,000th. Good, so we've got n of these particles in a box, and the particles collide with the walls. Collide with the walls. And we're going to say they are elastic collisions and see what happens. We're just going to follow our ideas. What happens when particles are colliding with the wall? So we have impulse. So remember chapter 6 on collisions, coming back to haunt us. So we have impulse, we have F times delta T is delta P is equal to M times delta V, or I can write F delta T is equal to M V final minus V initial. Now what we're going to think of is a particle that starts here, bounces over here, and bounces back again. Okay, hits the wall, bounces back. So since it's doing that, then what we have is M times 2V if it's an elastic collision. Elastic. Okay, M2V because 1V and then minus negative V. Okay, what about the delta T? Well, we can say that V times delta T, speed times time is a distance, and we're going to say that's 2 times L because the particle's flying, hitting the wall, and flying back again. So the delta T for each of these collisions is as given right here, and we can take this up to the top of the board. So now we have F, the delta T is equal to 2L over V, so F 2L over V is equal to M times 2V, and that simplifies to, with the 2's canceling, we get FL is equal to MV squared by cross multiplying over, okay? FL is equal to MV squared. Now this is all happening in the X direction, so I'm going to call this, Fx delta Px Vx. I can put x's on all of these things here. So Vx squared, okay? Next, I'm going to divide by L squared, just because I can. In fact, no, I'm going to divide by L cubed. L cubed. So on this side I have L over L cubed, so I have F over L squared is equal to M Vx squared over L cubed. And force per area is pressure. So this is the pressure, at least dimensionally, due to these collisions, because there's more than one particle, there are many, so each individual one, we have the pressure, M Vx squared over L cubed, which is volume, so we're going to have pressure times volume is equal to M Vx squared. And so far this is actually just a little infinitesimal because we're talking about atoms here, but we're going to sum them up in a second. So let's leave the picture here. Okay. So next we're going to sum. So we're going to do a summation, and then what we're going to have is the sum of all these M Vx squared is going to be pressure times volume. As an infinitesimal, this could have been D pressure, but we'll just keep it at pressure there. The summation gives us the true full pressure and volume. And the next thing we can do is for X, Y, and Z, we do the same thing for X, Y, and Z now. This was just an X, then we have the summation of M Vx squared plus Vy squared plus Vz squared E times V. But since we had all three of these, we're going to have to divide this by 3. And we're saying this is a lot of random activity going on here. And then this summation goes to n for the total number of particles. And this is the average of v squared in 3 dimensions. Okay, the average of v squared, so what we end up with is n m v squared average over 3 is equal to P times V. Okay. So now we're not saying all the speeds are the same, they're not all the same everywhere, but you average them all up and you get this average for all of these individual speeds. So now we're ready to draw our conclusion. Because that has a look like the PV of the ideal gas law. So here we go. Okay, we're going to have P times V is equal to N M V squared average over 3. Okay, so what belongs on the right side of the ideal gas law? N, and now I'm going to introduce something called the Boltzmann constant, and T, NK Boltzmann T. Okay. So this is the number of particles. That was in our original derivation. What we're claiming is that this Boltzmann constant, Boltzmann times T, what we're saying is the pressure times volume is proportional to the number of particles, the number of individual particles times this universal constant times T. So you look up the Boltzmann constant in your book, and we find, what do we find for the Boltzmann constant here? Well, if we don't find it here, it will happen in the book. Okay, we'll fill that in later. It's in all these books, of course. I wanted to have it now. Ah yes, 1.38 times 10 to the minus 23. 1.38 times 10 to the minus 23. Very small. And the units are joules per Kelvin, which you get from a dimensional analysis of this, okay? Because this is just a number, and this has the units of energy. So if this is Kelvin, then this is joules per Kelvin, okay? Okay, so there's our ideal gas law from a physicist's point of view. And there's a really interesting corollary to this having to do with the speed of the molecular speeds of these gas particles. For one thing, if you look at these two expressions above each other, you can see that the absolute zero of temperature would correspond to motionless particles. All molecular motion ceases. So higher temperatures are associated with molecular agitation, okay, molecular motion, and we can actually identify these two quantities and get the speed of gas particles. So I'll put that as the last little point here on this section. Yeah, this derivation is interesting because it's only making use of things that we've studied this semester. Okay, well, then we take a few averages. I haven't studied averages that much. But otherwise, the collisions and the energy and so forth, things that we've studied, all the dimensional analysis we've studied before. So yeah, let's see what we get here. We're going to identify what's after the n in both of these. So we have K Boltzmann times T, and you'll notice that's a very small number. 1.38, 10 to the minus 23, you know, a couple hundred in temperature is still not going to make that large, so you'll be 10 to the minus 20, 21. Okay, so what do we have here? K Boltzmann T is equal to M over 3, and let's just go ahead and solve for B. So B, and this is called the root mean square. I'll just write that down, root mean square is equal to the square root of 3 K Boltzmann temperature in Kelvin divided by M. So yeah, this is something you guys should have a look at. Namely, I'll see if we get a good problem in the book there. What you'll find is that gas particles at room temperature, so the gas particles in the room that you're standing in, you know, oxygen, nitrogen, what have you, they'll be moving at speeds of hundreds of meters per second. Okay, they're moving very rapidly, even though we don't see them or feel them. They're buzzing around, so to speak. And again, to bring the temperature down means to lower those speeds, okay? To bring the temperature down here, the speeds are lowered. So this is what was called the kinetic theory of the ideal gas. So let's make sure we have that here before we go on. Kinetic theory of the ideal gas. Now, you're thinking or you're not thinking that how are we going to deal with this on the exam with no calculators if we have these kinds of numbers, the square roots and so forth. And what we're going to do for the ideal gas, I'll assign a couple of these on the homework, but what we'll do on the exam is use an interesting simple version of the ideal gas law, namely where we just consider N and K Boltzmann, number of particles, to be constant, and this is a constant anyway. So I think I'll get to that next. Let's see how much time we've got going here. Oh, we can go a bit longer. Okay, so far so good. This was all just to show that the ideal gas law follows from classical mechanics and the ideas of classical mechanics, along with the idea of atomism. So by the way, this was one of the big triumphs of classical mechanics. This was toward the end of the 19th century when these things were done. And, you know, we've talked about Newton's law of gravity and the motion of the planets. Well, the motion of the planets was a spectacular example of applying Newton's law and understanding the universe. This was another spectacular example because these atoms had not been seen. And yet this behavior is well verified. And so classical mechanics was just applied to microscopic particles and came up with the well-verified formulas. Okay, so how are we going to use the ideal gas law? Now that we've done this, let's just give a couple of examples. How we're going to use this here. In fact, I'm going to assign this as a homework problem. Imagine this is the water. So we had something like that on our exam. You know, you got a fish swimming down here. Okay. And there's a little bubble released, and as it goes up and breaks the surface, it has increased its volume because the pressure has decreased, right? Higher pressure, lower pressure. And just suppose the temperature is T in Kelvin, then what we can do with the ideal gas law, we can say PV, what's the best way to do this? Yeah, PV over T is equal to the number of particles in the bubble. Okay, Boltzmann is equal to a constant. Okay, so if this is equal to a constant, then it's the same constant down here as it is up here. So what we'll get is, if I label this 1 and this 2, we'll get P1 V1 over T1 is equal to P2 V2 over T2. Okay. And again, temperature in Kelvin. Temperature in Kelvin, and if you want to simplify this, you say the temperature is the same, you know, down at the bottom and the top, and then these two temperatures are the same, and then you'd have P1 V1 equals P2 V2. Okay. So the homework problem we're going to have assigned. Here, I'm going to erase this. By the way, so we can use the ideal gas law for these two states here. And, you know, so the way we do energy and momentum, we label a place 1 and a place 2, or A and B, and then we have this one expression. So in that sense, we have a good recipe for working problems like this. And since I'm not going to do the whole thing for you, in our homework problem here, let T1 equal T2, because then it cancels out of the problem. P1 is equal to P atmosphere plus rho GH. So apparently we need to have a depth here. Okay. And P2, since that's right when it comes up to the surface, is just equal to P atmosphere. Yeah, those are the ingredients. You should be able to do this no problem. And that's the type of problem I'd like to be able to put on an exam. There's a few others of this type. They keep us from having to deal with these numbers right here. And very useful. Okay, so that would be the ideal gas law. In addition to that, I'm going to look up in the book a couple of other problems here. Oh, this stuff was written down somewhere. And yeah, actually I had quite a list here for you. Maybe a little too much. Let's see. I will thin those down a bit. Let's see. So this is in chapter 10. And we have to do a few things. So got some temperature conversions, got some linear expansion, and we have that one I just talked about. Okay. Here, let me write our homework down for us and we'll call it a day. And so, yeah, this you want to either work into your notes or separately. This is Friday the 24th is when that's due. So homework, chapter 10, and what do we have? We have 7 and 9. These are just trivial temperature conversions, more just to look at them and see what's going on. We have 12, which is thermal expansion. And then I wanted to leave a couple of these out, didn't I? But this is a very clever thermal expansion problem right there. I think you'll enjoy that. Gap in a ring. And then we'll add one more, namely that air bubble I was just talking about, 39. So these two are nothing and these three are a little interesting for you, okay? So as always, keep taking good notes and collect them all, turn them in on the 24th, and see you next time.